All right, we're here at Algebra II, section 521. So today we're going to be still talking about inverses, not as our main focus as much, but one specific type of inverse. So to start off, we have 8 different parent functions, which we should be fairly familiar with at this point, right? So what I want you to go ahead and do is you're going to pause the video, and then you're going to go through these 8 parent functions. First, see if you can find the equation of the inverse. Now there will be 2 of them which you can't, but just try and see which ones those are. And then graph the parent function, and then also graph the inverse. You don't need to have the graph be some super amazing graph, just a quick sketch, because you should have a general idea of what these graphs look like. And then for their inverses, again, it's the reflection over the line y is equal to x. So go ahead, pause the video, try that out, and then come back here and we'll talk about those. All right, so what we should notice is that for some of these, our parent functions gave us the inverse itself. So the parent function was its own inverse, which is kind of a rare case, but a very, very special case. So which ones of those were number 3 here, where it says y is equal to x. And that kind of makes sense because it's reflected over itself, so it doesn't change. Right? The other one here, the rational function of 1 over x, that is also going to be its own inverse. And then last one here, this circle, is going to be its own inverse. So that circle, so long as it's centered on the origin, is always going to be its own inverse because it's a circle reflected over a line through the middle of that circle. So that's kind of interesting stuff, but the more important ones are the ones we can't do, or we can't write the equation for. So the first one of those is probably the absolute value function. Now we can't really do that because we don't really have the tools to have an inverse of an absolute value, because they're kind of a weird operation. There is a way to do it, but it's not very intuitive for us. But the one that we're going to focus on primarily is actually the exponential, right? So I can change it and make it x is equal to b raised to the y power, but I can't get y by itself. So I can get the inverse, but not in the form y is equal to. So that's our biggest issue. So to take a look at this and figure out, well, how can we do this, we're going to make a xy table. So let me go ahead and grab my document camera, and we'll do that real briefly here. Some zoom for me. Awesome. Okay, so if we make a table for y equals 3 to the x, I do my little table for x and y. I'm going to do from negative 3 down to positive 3. So if I plug that in, well, 0 is going to be 1, 1 is going to be 3, 9, 27. Negative exponents just cause me to flip my fraction. So that's going to be 1/3, and then 1/9, and then 1/27. Right? Well, what if I want the inverse? Well, the inverse is x is equal to 3 to the y power. So I can get that table without having to try and plug things in, because that's a little bit more challenging, by just taking the reciprocals, or not reciprocals, the transpose of all of these, right? So I would have now the point 1/27, negative 3, and the point 1/9, negative 2, and the point 1/3, negative 1, and then the point 3/1, 9/2, and 27/3. So let's go ahead and plot those points and see what that looks like. So if I draw my axes, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 1, 2, 3, 4. Plugging these out, I cross through here. Or I missed a point here, didn't I? Yeah, I missed the point 1, 0. There we go. Point 1, 0, 3, 1, 9, 2, and then I got dink, dink, dink. So I got these points here. So I effectively see this shape. So if I try and graph it, I'll do it in a highlighter just to kind of see it a little bit more distinctly. Right, we're kind of falling there, and then we're kind of going up, then curving over. Right, so we're creating that kind of a shape out of our graph, which makes sense because this is a reflection over the y is equal to x of our exponential curve, which would look something kind of like that. So we are getting that same shape. Now, a few things to kind of note on it. We do kind of follow this asymptote down. That's because we can't ever get a 0 or a negative out of this. Because it doesn't matter what I take 3 and raise it to as far as powers go, I can never get negatives or zeros, right? So I end up with this kind of a shape here. That is our shape that we're going to be talking about more in the future here. Okay, so we now have a graph for it, but we still don't have an equation for it. So that's our next goal, is to figure out, well, how can I get an equation? So my next question is, well, let's go back to our inverse. And what if I were to make my inverse have an input of 81? So x equals 81. So then what would my y be? Right. So I could plug in 81, and I would get 81 equals 3 raised to the y power. Now I can't, with my current tools, get y by itself. Right? I just don't have the tools to do that right now. But I could try and figure it out. So what I want you to do is pause the video and try to figure out what y has to be to make that true. Okay, so what you likely did was you said, well, 3 raised to what power is 81? Well, 3 raised to the first power is 3. The second power is 9. The third power is 27. It's the fourth power, which gives me 81. So then y equals 4. So I could add a point here, the point 81, 4 on my table. Okay. So the most important thing there was your thought process. 3 raised to what power equals 81? And I want you to keep that in mind for this very next problem. All right, so let's take a look at this. So this is called the ancient puzzle, right? So this is actually legitimately an ancient puzzle. It's not written in the same way because, of course, the ancient Indians did not use LOG for their letter system, but you get the point. So what I want you to first do is find the pattern. So all 4 of these are solved out. So try and find what the pattern is between these numbers and their orientation. My hint to you is what we just did matters. Okay. Once you think you've found this, then go down to A through F and try and use that pattern to find what the question mark would end up being. So go ahead and pause the video, try that out. All right, so the pattern you should have found is that 2 raised to the third power equals 8. 5 raised to the second power equals 25. 3 raised to the third power is 27. And 10 raised to the fourth power equals 10,000. Okay, so that is the pattern for this puzzle. Okay. So if I go down to A, I would say, well, this is me asking 2 raised to what power is 14? Well, it's going to be to the fourth power. Right? And then we have 2 raised to what power is 32? Well, that's the fifth power. So then here it's what raised to the second power is 100? Well, that's 10. 5 raised to the third power equals what? Well, that's 125. And then what raised to the fourth power is 81? That's 3. And then lastly here, 100 raised to the what power equals 10. And that would be the 1/2, because again, 1/2 power is the same as the square root, if you recall that from previous courses. So that's our pattern, and that's effectively what we're trying to kind of get here, right? So I'll kind of spoil what these are, but these are called logarithms, and they are the inverses of exponential functions. Okay, so if we look at the last part here and say, well, let's try and rewrite our inverse from the first problem with this kind of logarithm stuff. So let me hop back over to this view. So we were looking at this. Well, with all of those patterns, I'm going to do that general case thing. I'm going to say, well, log base b of a equals c. So how could if I wanted to write this as an exponent, the pattern we saw was this raised to this equals this. So b raised to the c equals a. Now let's take this, and using this pattern, as opposed to going from a logarithm to an exponential, we're going to go from this exponential to this logarithm. So that would be log base 3, because those match up, and then of the outside, which is going to be x here, equals y. And now my inverse has y by itself. So I've finally been able to do it. And that's what logarithms do, right? They give us an inverse for exponentials, which is something we haven't had in the past. Now, they are extremely useful beyond that, but that is where they initiate from. So that is our main crux today, just kind of our introduction to these logarithms and kind of how they work as the inverses of exponentials. Here is our homework, 60 through 67, and I will talk to you guys next time.